Okay, guys, finally on the last part of BAP, Lab 5, all right, where we're talking about classification. I introduce it. Um, I created a second slide. I didn't want to append it to the existing one. It just kept getting bigger and bigger and bigger, so I just called this Lab 5 Part 2. You can grab it from Blackboard. And if you remember where we left off in our code, right here, we started doing the multi-classes. All right, we just jumped into multi-classes. We talked about one versus one versus all. We talked about how certain algorithms, they prefer one over the other, right? One versus one versus all. We went ahead and we took our data train data and we actually went ahead and we fitted it. Basically, we trained it using that fit function on the actual target train data. So let me just do this again. And you see it's running. Excellent. No errors. There's warnings, but that's okay. And I'm going to go ahead and predict this. Let me make this slightly bigger. It's easier to see on the screens. And I'm going to predict some digit. Now, some digit, if you remember, I think in my slides I had 7 the first time I ran it. Now I have 4. Ugh. So it's still not right. If you remember, some digit for us was what? It was 9. It was 9. It's actually 9 for us. So poor prediction, right? I wonder how it worked for you guys. But for me, it was poor prediction. All right, a little disappointed, but it's okay. So we worked through. Okay, so from here, right, let's get the scores. Let's check out what the scores are. So I'm going to go ahead, run the decision function. Now you've seen me get the scores before using the cross-val function, but we can go ahead and just, instead of doing, when we're doing the k-fold, we can get the scores, but I can just get the scores flat out also, just using this dot decision function method, right? So I don't have to do a k-fold analysis to grab it. So fix that up right there, boom, boom. All right. So I'm going to get the scores just for the digit, that one digit I ran. All right. And again, how do we know that it's going to be 1 versus all? Because when I run this scores, notice I don't get just one score. No. I get, it's hard to see here, but I get 10 scores. 1, 2, 3. Let me go ahead and copy this. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 scores. Why do I get 10 scores? Because, like we said before, the SGD classifier, right, it automatically runs 1 versus all. So basically what that means is it runs just like we did previously with the 5, training the 5 and not training the 5, right? We had a binary classifier. Well, we created 10 binary classifiers, 1 for each digit, 0, 1, 2, 3, 4, 5, 6, 7. So for each one of them, it created a score for the binary classification problem it did. It created a score for each one of those, in this case, this image, right? And the way it works now when you have a multi-classifier using 1 versus all, it's just going to take the highest score, guys, right? Because now it ran the binary classifiers for each one. So for example, the first one, 0. Is it 0? Is it not 0, right? So, but instead of taking the prediction, it gives the score, right? The score. Just like we did before with our binary classifiers when we checked out the score. And so it does it for each binary classifier, the 1, the 2, the 3, the 4, gives you all the scores back and it takes the highest one. Notice they're all negative, by the way. And here, how do we know which one is the highest score? I mean, we can just eyeball it, but we can also use a nifty little function from NumPy called np.argmax. And what argmax does, it literally gives you not the maximum value, that would be max. Argmax simply gives you the maximum value of scores. And as you can see over here, the answer is 4. So if I go to literally 0, 1, 2, 3, 4, sorry, 0, 1, 2, 3, right here, 3, 4, the fourth value. So the fourth value would be 0, 1, 2, 3, 4. So it's saying this value right here is the highest value right here. I'm sorry, can't count. This one right here, that's the fourth value, okay? How is that the highest value? They're all negative, okay? So this is actually the smallest negative number. Remember your math, right? When it comes to negatives, the smaller the negative, the higher the value. So this right here is our highest value. It's the fourth value, and therefore whatever, this is why it was classified as 4. Now, it just so happens that our classes I line up perfectly as 1, 2, 3, 4. And again, in my slides, it was the 7th one, right? It was the 7th one. So, but how do we know that this value corresponds to which class? Well, I mean, we can obviously, we know it's going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, but let's say you didn't know that. We have this nifty little method right here called classes, and it'll tell you. All right, and over here in your output, you see what? You see this output. It gives you the output of all the classes that your multi-class classifier is predicting, right? And it gives you the order right here, 0, 0, 1, 2, 3, 4. The fourth class was the highest value. What's the fourth class? 0, 1, 2, 3, 4, right? And that's basically how the classifier works, the multi-class classifier in this case, when it's doing 1 versus all. All right. Now, I don't know about you guys, but I didn't get the right result. A little bummed about that, all right? What if I suspect that, you know what? 1 versus all got all messed up, but what if we did 1 versus 1? All right, what if we did 1 versus 1? We can actually, by default, the STD classifier does 1 versus all, but we can actually choose which methodology each classifier will use in a multi-class setting. We can force, for example, STD classifier to use the 1 versus 1 method, right? And also vice versa. If there's a classifier that by default uses the 1 versus 1 method, we can force to use the 1 versus all method as well. In this case, we're going to force a 1 versus 1 classifier. So here, let me import my 1 versus 1 classifier method. Explicitly, I'm calling this explicitly. Let me comment these guys out so I don't get errors. All right. I'll go ahead, import that bad boy, and let us begin. Okay, let us use it. Now watch how I use this. All right, watch how I use this. All right, I'm gonna go ahead just for ease. Let me go ahead and grab the SGD classifier up here when I used it the first time. Right here. I'll take this right here, copy that down. And I'm doing this just to show you what's basically happening. So before we declared the SGD classifier, and again, with the random underscore state, we didn't have to do that. This is just so when you're running the analysis over and over again, you get consistent random numbers. Okay, consistent random numbers, right? But in all honesty, when we're actually doing our class, when we're running this algorithm, we'd run it multiple times, we would let the randomness just go wild. So right here, this is when I declare my SGD classifier. Now, all I'm doing is I'm wrapping the classifier in this method right here. Or I mean, it's more than a method, it's a class, but that's a different conversation. So here, I'm wrapping it in 1 versus 1 classifier, right? And I'm setting this, creating a whole new variable called OVO. All right, now why am I doing this? What's the logic behind this? The logic behind this is that it's saying, okay, you want me to run a 1 versus 1 classifier? No problem, I'll do it. Which classifier am I going to enforce that on? The SGD classifier. That's the logic behind it. That's basically how Scikit-Learn works, because it does it that way just so you have the flexibility to put any classifier in here if you want to force 1 versus 1 classifier. Or not any, but mostly any. I'll say mostly any, and you'll see what I'm talking about in a moment. So here, I have a new classifier that's programmed, a 1 versus 1 SGD classifier, right? Call that OVO. Nice and easy. From here, I'm going to do everything I did before. I'm going to go ahead and fit the data, right? I'm going to do a fit. I'm going to do predict. But instead of using the SGD variable, I'm going to use, that's going to end up being a do a 1 versus all. I'm going to do the 1 versus all right here, which forces the 1 versus 1. Run this, see what's going on here to your right side. Notice it's still running, huh? Notice it's still running, and finally finished. Right, no errors, some future warnings, no problem. Now let me predict. Boom. See your results you guys got? If you had a wrong result like I did, I had 4, now I got 9. Why? This time, it's going to every image. And instead of asking the image, hey, are you a 0 or are you not a 0? Or are you a 1 or are you not a 1? It's basically what it's doing is dueling 1 versus 1. So it goes to, for instance, the first image and it says, hey, are you a 0 or are you a 1? Okay. And then it asks, are you a 0 or are you a 2? Okay. Are you a 0 or are you a 3? Are you a 0 or are you a 4? It's doing 1 on 1 on 1. And after it does all these duels, right, the class that wins the most duels, so hypothetically in this case 9, it was basically 9 versus 0, 9 versus 1, 9 versus 2, 9 versus 3, 9 versus 4, etc., etc. What happened was, because 9, the class 9, was winning most of the duels, right, in these one-on-one sessions, the classifier, the 1 versus 1 classifier, all right, cool, 9 is winning most of the one-on-one duels. Therefore, this image is a 9. That's how it works, right? And there's a little method here called estimators, right? And we can verify basically how many times, estimators is basically how many times those one-off duels ran, and we can basically verify explicitly here that yes, indeed, 45 times. There was one versus 1 duels 45 times, if you see that. Okay. Now, let's run the decision function on this, on OVO, on the sum digit. Remember, the decision function gives you the scores, right? And what are we going to get? I need to store it. OVO, decision function on that sum digit. And again, you'll notice we get 1, 2, 3, 4, 5, 10 scores. Right? We get 10 scores. Right? Okay, so we have 10 values, 10 scores. All right. Now, why do we have 10? We ran this thing 45 times. What is this actually? This is actually the amount of times the particular class won the duel versus the other classes, right? So, okay, that sounds fair. What's with the decimal places then? What's going on here? You see, when it counts who won the duel or not, a lot of times it doesn't give you one number. Like if 9 dueled against 0, it doesn't say, okay, 9 won. That's one victory for 9, right? There is obviously a range of error in the duel, and it takes into account that range of the range of error. So you're basically seeing like more of a normalized number than anything else. The normalized numbers than anything else. Why does this do this? What if there's a tie? What if there's a tie, right? It does this so that there's a difference between victory. So let's say 9 dueled with 0. And in this case, this is 9 right here. This is the last value, the 9th value. And look, we can see it's the largest number, right? We can see it's the largest amount of wins. But look at this. It's damn close to this value. What is this? 0, 1, 2, 3, 4. Ah, right? The second highest number is 4, right? Which goes to leads to tell us why I got 4, at least in my case, right? So here, right, they probably won the same amount. It was on the fence. But the victories in the 1 and the victories in the 1 versus 1 duels in 9 were probably slightly stronger, which is why it is slightly more than this one. That's why you see these decimal places, right? Because the duels, it's not simply you won, you lost, right? If you want to think of a basketball game, there's a difference between if LeBron James plays, if the Lakers play, let's say, give me a good team here. If the Lakers play the Clippers, and the Lakers win by 101 to 100, versus the Lakers play the Knicks and they win 150 versus 10, which, by the way, in this day and age is not really ridiculous. All right, so there's a difference in the victories. That's why you have these decimal places. They take a normalized score versus a discrete score of 1, 2, 3, whatever. So that's why we get in those values. All right, and it worked out perfectly. In our example, it worked out perfectly because, I mean, that was a tight, but we got the right answer. All right, so from here, let's go flip back to our other one, our SGD one we trained for multiply classifier. And let's get the cross-val score. All right, let's go ahead and get the accuracy like we did before. Like we did before for our binaries. Let's go ahead and do it. So I'm going to go ahead and grab my cross-val score. A k-fold. Remember, I'm now doing the k-fold analysis, and I want accuracy. Here we go. And I'm going to do the same, get the same analytics like I did, measures and analytics like I did before on this multi-strategy. All right. All right, and SGD, data train, target train. This is different because we actually now we're doing it on the all the data set, all the values. We'll do a k-fold 3, and again we're gonna break up the data set in 3 parts and run the analysis, and let's do it. It's running. All right, I got my results, and you know what? It's not bad. It's not bad. It's in the 86, basically 86%, 86%. All right. Next step. Let's go ahead and get our precision and recall for our multi-class analysis. Let's go ahead and get the precision and recall. Now, for precision and recall, I'm going to import pandas up in here to make it nice and clean. Remember, firstly, we need our predictions, right? We need our predictions because we basically have our actual values in our target train data, but we need what we predicted for the actual values. Because remember, when we do precision and recall, those kind of measures, right, those kind of analytics, you need a confusion matrix, right? So to get a confusion matrix, you need the actual values and you need the predicted values. So first things first, let me import pandas, and you guys will see why I import pandas in a second. It's just easier to view the data side by side. Finally, bring a pandas back in a limited role. Get rid of that. Alrighty. And let's do cross-val predict, baby. Let me go ahead and grab the, it's faster if I just do control find, cross-val predict. Oh, there we are. Just copy it right here. All right, and this time I'm going to call this predict M M stands for multi-classes. All right. So it's going to be SGD, yes. SGD, data train, yes. But now it's going to be target train, not target train underscore 5, all the classes. And again, CV3, I want this to be a 3K-fold analysis. All right, I get the predictions. Running, done. All right, so I got my prediction scores, right? And if you type in your predict MM over here, you'll see you get a whole bunch of values. And we want to see how those predictions did, right? We want to see how our precision and recall did. All right, now, here, when you have a multi-class analysis, your precision score, all right, I'll grab the, right here, if you remember, your precision score, it was very easy. We simply gave the target, the actual data and the predicted data, and it gave us a precision and we gave us a recall, right? We have to add another parameter when we're doing a multi-class analysis. We have to add another parameter when we had a multi-class analysis. I once had a student where they asked this question and the student got it wrong. Because the student never actually, they read about multi-class multi-class classifiers and Scikit-Learn, but they never ran it. So if you ran it, you would have known that this is and this is another one of those gotcha questions. But when you do precision and recall on a multi-class classification, you have to add a third parameter called average. Why? I mean, this makes sense because now you're getting multiple precisions and recalls back, right? So do you want all the value? Basically, the function is asking, listen, do you want all the values back or do you want an average, right? In our case, let's give us all the values. Let's check them out, right? So I'm going to say average equals none. No quotes, no nothing. Remember, in Python, none means null. All right, none. And this is going to give me what? It's going to give me back the precision score for each class. And it's going to same thing with recall. I'm going to go ahead and save this in a variable PS RS. Whoa. I didn't change the parameters here. It's now target train. My bad. And it's not predict 5, it's predict M. Right, so we're running it. Our actual data is now going to be the actual classes, and our prediction is going to be the multi-classes. Now I can go ahead and run this. Boom, I got my precision recall score. And this is where I bust out with pandas now, guys, because you know what? Let's just look at a table. It's just much easier, right? I have the table right here. And I'm going to call this good old df equals p.data frame. I'm going to make the precision column and the recall one. You know what? Just to get back to some normalcy here. df, here's my df. I click on it, and here's my precision recall. And you guys can see it. Same thing here, right? It looks like it basically, yeah, it's basically the same thing, right? Basically the same thing here in my slide. So, all right. The measures for, if we look at 3, the precision was low. 5, the recall was low. 8, the precision was low. All right. Not to say that the other stuff was too hot, right? Some of them was pretty good. 0 was fine. 1 and 0 seemed to be fine, both in precision and recall. 2, precision was good. Recall started going down in the 80s, but clearly we can see from the reds here, see the reds, that both precision for 3, recall for 5, and 8 were kind of off. Okay. Now, by the way, we keep talking about those color maps, and I got questions about the color maps. This is what the color maps do. The color maps, Spider takes full advantage of this. The color maps is a range of colors, and you could choose which range of colors you want. This is one particular range of colors, and you see how the magnitude of the number gives a different color, right? Right off the bat, we saw where the smallest numbers were, the reds over here, or whatever you want to call these colors, right? And we see where the highest numbers are, the dark blues right here. Boom, boom, okay? That is the power of color maps. That's what Matplotlib does. Any set of numbers, any, not even images, any kind of analysis you're doing, you can scale that. You can attach the scale and the difference in the magnitude of the numeric values to a color so it catches the difference in the values of these numbers, catches your eye much faster. Visual analytics, my ABI students, that is visual analytics in play right there. Full force. Okay? Now look, we can also get the averages, right? There's a couple of different averages we can get if we wanted to. If you want the simple mean average, right, you can do what we call the macro. If you wanted to do a mathematical average, right, we can do, based on the confusion matrix itself, we can use the micro one, all right? So let me show you the example, and then I'll show you the actual score, right? So what does macro mean? Macro mean is basically, you basically take the precision, like this is an example, precision example going on right here, right? Precision example. You basically, let's say we have a 3x3 confusion matrix, so only 3 classes, right? Again, remember, when you have a confusion matrix, your rows are your actual answers, your columns are your predicted values, okay? So the precision for class 1 was going to be what? If you remember your formula, it was basically your true positives divided by your true positives plus your, in this case, what is this? This is it's predicted to be positive, but it's actually not positive, so it's a false positive. So your precision is your true positive divided by your true positives plus your false positives. So in this case, for class 1, the precision would be 1 divided by 6, 1/6. For class 2, it would be 2, this is the true positive part right here, divided by 2, the sum of the whole column, which is 2. And the precision for the third one would be, this one right here is a true positive, 1 divided by the whole column, which is 2, okay? And if I add up all these fractions and divide by 3, I'm basically taking the mean. I'm taking the straight up mean, arithmetic mean of the 3 positions, I get 0.56. So that's what a macro average is. That's what a macro average is. If that's a macro average, what is a micro average? The micro average is you actually go ahead and do the math for the precision, right? So what is, for the overall confusion matrix, what is the precision? What are all the true positives? So the numerators are all the true positives. This is my true positive. The true positives are always on the diagonal line. This one, and this one. 4, that's my numerator is 4. And then what's my denominator? My denominator is going to be everything, right? It's going to be the whole matrix, the summation of the whole matrix. 1 plus 1 plus 4 plus 2 plus 1 plus 1, which gives you 10. 4 divided by 10, and it gives you 40%, okay? So that's the difference between the two averages. We can go ahead and do that. Right? So I can literally just go ahead and grab the running for both of them, and you can see the averages. First, let's do the macro, which is and when you run these, please put them in quotes. Macro is just a simple mean of the values. Literally, it's like we took our data table and we just took the mean of the columns. All right. So here, I don't want to overwrite those variables. .866 was the precision, and the recall was 0.86. Okay, all right. Again, not bad, not bad. If we do it again for the micros, again, if we do the math, we calculate precision recall using the whole matrix, roughly 0.86. So they're both the same. Roughly, they're both the same, all right? Okay, not bad. You know what? Not bad at all. Multi-classifier is not bad. All right. Now, let's go ahead and do the same fitting, this time for random forest classifier. Remember? It's that simple, jump from one classifier to another. We already have our RFC previously defined. I'm going to go ahead and fit and predict it. So I'm just going to grab the SGD right here and predict. I'm going to rework the models. It's so easy. So I named my random forest classifier RFC. So whatever you guys named it, please just use that. Watch this, guys. Watch this. Look, check out how the random forest one. Oh, actually, that wasn't that bad. It wasn't that slow. The first time I ran, it was kind of slow. All right, now let me do the prediction. All right. And I got the answer 9. Woohoo! All right, go random forest. All right, I got the answer 9. Now, the correct value was predicted. In this case, and this is why I say mostly, very carefully, I said mostly classifiers, they use 1 versus all or 1 versus 1. In this case, neither are used because the random forest classifiers they directly classify the data into multiple classes. That's the way that algorithm works. In addition, recall that we can view the probability for each instance, right? When we call predict proba underscore proba, we can get the probability that random class said that each image was a, remember it gives you probabilities for which class that number or that image belongs to. We can do the same thing again. In this case, do RFC. For proba. And stick in some digit over here. All right, and the results you get over here are the same results as you get over here. And I just clarify it, 10, 10, excellent. Okay, excellent. So here, what is it saying? It's saying it's 80% confident that what? That it's 9. Again, you know what the classes are. If you type in the classes, it'll tell you which class that probably belongs to. So it's 85% confident that the value is 9. Fantastic, fantastic. And it's 10% confident that the value is either 4 or 7. Oh, that's interesting. That's interesting because in my slides, when I ran this analysis for the stochastic gradient classifier, I got the answer 7 without doing the 1 versus 1. And again, when I did it here, I'm doing it in the code in front of you guys, I got 4. Notice those are the only ones that had any kind of non-zero probability. Very interesting. Very interesting, right? So again, random forest classifiers, they're sweet in the sense that, hey, they don't use 1 versus all or 1 versus 1. They directly classify into multiple classes. That's how they work. Now let's go ahead and do the same thing before. Let's go ahead and calculate in this case we didn't do, I guess I didn't do the accuracy, but fine. Let's go ahead and calculate the precision and recall for the random forest classifier. Okay, so let's go ahead and do that. Basically, and I'll do the one for, I'm literally going to just copy and paste this, guys. Right. I'm going to do the one, I'm not going to take the average, I'm going to take the table again. All right. And again, I'm going to predict, but this time I'm going to call this predict RF for random. Let's see what variable I used here. Yep, excellent. Predict RF for random variable. I'm going to put RFC in here. I'm doing a k-fold test, 3 k-fold. Notice, by the way, we have yet to touch the test data. Notice that? We have yet to touch it. Doing the predictions, doing the predictions. Boom, I got my predictions. All right, now here, I'm going to change this to be P, what did I call the variables here? Oh God, such a long name. My training data is still the same. My actual data is still the same. My predictions have just changed. All right. And here, and this, I called it DFRF. Makes sense. Boom. All right, I got a new table, DFRF. I go up here, I click on it, look at my results. Boom. In fact, I think I put the results side by side, did I? All right. So here, I mean, I didn't actually, no, I didn't put those results side by side. I did the one versus one results side by side. We'll do that in a second. But look at the random forest versus the stochastic gradient descent one. My God, people. See the difference? Look at the reds now. Before, in the previous table, the reds were at like 70%. The reds here now at 90%, 91, 8.89, 90. Look at our dark blues, 98, 98. Again, 0 and 1s are fantastic, right? But aside from the recall for image 8, everything is in the 90s. Random forest classifier, guys. Woo! What's up with that? What's up with that classifier? Guy, just goes to the fact that certain analysis lend itself to certain classifiers, right? Certain classifiers lend themselves to certain analysis. You will learn more about it, or you have learned more about this, or you're learning more about this in your deep learning or machine learning classes, right? Each classifier has a certain advantage over other ones. We talked about that a little bit before. Even just like how certain classifiers like makes sense to do one versus one versus all. Some problems are better suited for others. Random forest classifier in terms of multi-classification, like in a setting like this, it's good. As we can see, it's fantastic. All right, now here I'm saying, okay, these scores are fantastic. Let's compare the results to the OVO SGD classifier. The OVO SGD classifier. And again, I'm going to do the same thing I did with my random forest. I'm just going to do it now with the OVO. And again, if you guys remember what the OVO was, that was our SGD classifier all the way up here that we forced to be 1 versus 1. Let's do it. So I'm going to literally copy and paste again. All right. This is going to be now predict O. This is now going to be OVO, right? And by the way, I hope you're seeing now with the ease in Scikit-Learn, you can mess around your analysis across different classifiers. All right? You can play around with your analysis across different classifiers, experimenting, seeing what works, what doesn't work, what gives you certain kind of errors versus others. All right, so here, all right, it finally ran. All right, so here I'm going to change this to, I think I called them PSOs or anything. Excellent. All right, go ahead and run this. PSO. RSO. All right, cool. Click on the DFO table. Let's see the results. My eyes go straight to the reds and the blues. And the reds now, the lowest numbers are at 80%. Right? The blues are at 0.97. Again, look at 0 and 1, man. Living life. They're loving life over there. Some solid numbers for the zeros and ones. Go back to my slides, and I have a side-by-side right here, guys. I have a side-by-side, right? As we can see, even with the 1 versus 1 stochastic gradient descent classifier, the 1 versus 1, right? Again, 45 classifications happened. The random forest is better. in this analysis, the random forests, in terms of precision and recall. The random forest is better, man. The numbers are right in front of you guys, right? If we were running this analysis, I mean, if you were running this for a particular project, you'd be like, management, we should use a random forest classifier versus a 1 versus 1 stochastic gradient descent classifier. And management would turn to you and be like, yeah, what are you talking about? Right? So, but the point is, from an analysis point of view, I mean, this is you would make a decision here. Be like, hey, you know what? The random forest classifier seems like it's the best fit for the analysis I'm doing right now. But anyway, carrying along, all right? Carrying along. We're still not done with certain changes we can do, right? There's certain tricks we can do to help our analysis. Now, my ABI students, when we did clustering, you remember this. You remember this, right? When we were doing clustering, I said, listen, if you're doing clustering on value on different columns, different attributes, right, or dimensions, whatever you want to call them, and or features, that's what we should call them. But the range of numbers from feature to feature is different. It's gonna mess with your results, right? And I showed you guys that visually in ABI. Same thing in classification. It doesn't change. It doesn't change when you're doing machine learning. Clustering is part of it. It's another feature in machine learning. It doesn't. When you're doing classification, it's the same thing, right? So look, the accuracies are above 86%, and most of the precision recalls are over 80%. But can we improve this? Of course we can. A simple option is to scale the training data. All right. Feature scaling is an important part of transformation that you almost always do to your data when you're working with it. What does this fall under? This falls under data wrangling, but it's still very important in terms of your analysis. Machine learning algorithms, they won't perform well when your numerical features, in our case, we have pixel scores from 0 to 255, right? 0 to 255. If the scales are very different, if the range of numbers is very large, it won't work well on those machine learning algorithms, right? So for example, let's say we have a table with 2 columns, X and Y. X just goes from 6 to 39,320, and Y goes from, okay, I have a typo here. That shouldn't be a dash, that should be a 0 or a 1. So here I have a typo. I don't know what the heck this is. This should be from like 1 to 215 or 0 to 15, right? Now, which one has a smaller, concise range? Y does. Which one has a bigger range? X, right? This is going to affect our classifier results. We need to rejigger those numbers so that we have a smaller range of values. And again, in my world, in quantitative finance, we do this all the time when we're doing portfolio analysis or we're building quantitative research models or quantitative trading models, right? We always have to adjust that data because you can get wild results when your data has large magnitudes of scale. All right, and there's 2 common ways to scale: min-max scaling and standardization. So there's 2 different types of scaling, predominantly 2 different types of scaling. Let's start with min-max scaling, all right, which is sometimes called normalization as well. That's when you shift the values and rescale them so that the range of values becomes 0 to 1. No matter what your range of values were, right, you're going to shift it and rescale it so that all the values in your set go from 0 to 1. This is done by subtracting the minimum value and then dividing the max minus the minimum difference. All right. Obviously, Scikit-Learn has a class called min-max scaler with a parameter feature underscore range in case you want a range that's not 0 to 1. So in Scikit-Learn, you don't have to do 0 to 1. You can choose any range you want. It gives you that flexibility. Now, for example, how does this work? Let's say we have a column of values, 5, 8, 2, 6, 10, 4. First thing I do is I subtract the minimum value, which is obviously 2, from the value. So now I get an array 3, 6, 0, 4, 8, 2. All right? I just subtracted 2 from all these numbers. Now, I divide that difference between I divide these values by the difference between the maximum and the minimum values. What's the maximum value? It's 10. What's the minimum? It's 2. 10 minus 2 is what? It's 8. So I take these values where I already subtracted the min, and now I divide the difference between the max and the min from the original data. And so I'm basically going to be doing this math right here. And my new normalized values went from 582,610.4 to 0.375, 0.75, 0, 5, 1, 0.25. Again, notice I took that data, shifted, rescaled it, so now it's the ranges from 0 to 1. All right. The other one is standardization, right? And again, just like Scikit-Learn, we have a min-max scaler, we have a standardization one. That basically converts the values into their standard normal z-scores. Do you guys remember your standard normal z-scores? My ABI students better remember their standard normal z-scores, all right? That is basically when you take a number and you convert it into what we call the z-score, which fits into a standard normal distribution. If you remember, a standard normal distribution has a mean of 0, and it has a 1 standard deviation to the right, which is 1, and then another standard deviation to the left, which is -1. Basically, the unit of measure is just ones, the standard deviations. As they go in the normal distribution away from the mean, it's by 1, right? And you can take any set of values and convert them into essentially z-scores, or by doing standardization, right? That's basically what standardization is. You're going to convert these numbers into their z-scores. So, and this is why the average number, the value of those numbers will be 0. So let's look at this example, 582,610.5. All right, we start by subtracting the mean. Subtracting the mean from the data set. What is the mean of this number? The mean of this set of numbers is going to be 6, right? And we subtract 6 from these values, and we get -2, -4, 0, 4, -1. Nice. From this, we oh, sorry, this is a typo. This should be standard deviation, not variance. It should be standard deviation, not variance. We then divide the difference by the standard deviation, not the variance. The standard deviation in this case is 2.5, right? It's 2.5. And again, you guys can get this by simply using your NumPy function. So again, if I do, in case you don't believe me, if I copy and paste this, for example, A equals np.array. Okay. What's the mean? Stuff is all built in. That's beautiful. Not meme. Mean. It's 6. What's the standard deviation? It's 2.5. It's 2.51, blah, 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 all this stuff, but just to keep it simple, I use 2.5. Right? It's divided by each of these values by 2.5. All right? And I get standardized values that are these values right here, guys. Right? There's a 0 in there. There's all these other kind of values. Right? But again, it becomes a standard z-scores. So we rescaled everything. Right? Now, the benefit of standardization is that it's not affected by outliers. If you saw in the min-max scaling, everything has to be between 0 and 1, or whatever boundary you give it. Right? So if there is a very, very large number, if you have all these numbers and you have a very, very large number, right, then an outlier, it's going to affect the rest in the min-max scaling. It's going to affect all your values, the rest of your values to be extremely small, okay, extremely small. Standardization doesn't have this problem because standardization, it does not matter the size of the range of your values. They're just going to be converted into their standard z-score, no matter what that is. It could be within the first standard deviations, the second standard deviations, the third standard deviations. It could go beyond the third standard deviations, right? It's not really limited or bounded. Now, from our data earlier, remember when we used np.unique, we saw that we had a whole range of numbers from 0 to 55. Yes, we had that. But overwhelmingly, a majority of our numbers were zeros. We actually had very few high values in the 250s. They were there, but there were very few numbers, right? For that reason, we're going to use standardization to scale our arrays, right? And let's go ahead and do it. And basically, the way it works, guys, is very simple. We're first going to call it in. It's called our, right? And at this point, you should be in awe of all these packages built in Scikit-Learn. All right. All right. Imported my standard scaler. And now I'm going to go ahead and call this, copy and paste this. So perfect, that's not bad at all. I got my scalar object. I call it scalar. Again, you could call it anything you want. And I'm going to create a new data train container from my existing one. I'm not going to, if you notice, I'm not going to overwrite it. I'm going to keep my original data train values. I'm not going to overwrite it. I'm just creating another data container that's going to be scaled. Never overwrite your existing one. And there we go. Now I have another training set, but those values are now scaled. Those values are now scaled. Notice I'm not applying any scaling to my target data. I don't need to do that, right? That's fine. Those are just different classes we want to predict. It's the class, it's the data we're training to use the prediction, to do the prediction that we want to scale. So it's easier for the classifier. All right. Now, also from a mental note, guys, when you're doing the training, all right, when you're doing the training, let's see if I double click this. Let me take the first 5 rows of data train right here. Hold on. So 0, colon 5, whatever. All right, if I take the first 5 values, all right, I don't know if you guys can see this. Let me just copy and paste. All right, whatever, we're missing values. Anyway, whatever, fine. I'll get the point across. All right, you notice when it's training the data, remember, it's not applying the scaling within each image, across each image. Remember, each row is a different image. It's not doing that. What it's doing is doing it feature by feature. Each image has 784 features. This is one feature, this is feature 2, this is feature 3, etc., etc., etc. This is feature 784. So when the data is being trained, it's being trained feature by feature, meaning this column is being trained, this value right here is being trained among these values right here, the first pixels of each image, right? And then so on and so on and so on and so on. That's the way it's working. All right, that's the way it's working. That's how the scaling works. It works across the features, not across the images, right? Just so you can visualize it and understand that. All right, now let's go ahead and rerun our analysis on at least the stochastic gradient, but this time let's do it for our scaled training data, all right? And let me go ahead and grab it. I got it, so we can do this pretty fast. Boom, boom, boom. Oh, I don't even have it. Unbelievable. There we go. I do have it. Copy it. Bring it down. We're going to run it. But this time, SGD is fine. But notice I'm using my new scale training data now here, guys. Everything else the same. I'm using my new scale training data. There's the array. And you notice it's what? It's better, right? It's slightly higher. Before, I believe accuracy was in the 80s. If I have it up here, did I record? Yeah, the accuracy was in the 80s. Now, it went up a little bit into the 90s. All right, not bad, not bad. Let's go ahead and do the same thing with the precision and recall. Let's get the precision and recall and compare it. All right. So I have my precision recall right here. It's the beauty of just copy and pasting. So I'll do predict MS just to add the S over there. This will be S right here. Right, this now predict, that is the actual data is fine. This is my new prediction, and this I'll call this DFS, scaled, DSS, RSS. All right, here's my new values, and let's compare these values. I have them side by side here. Now, this table right here, look at the reds, boom, 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 right? This is our original SGD classification. This one is from the rescaled one, right? This is from the rescaled one, right? And as you can see, look at the reds. All right, the reds are already better, right? I believe the 1 versus 1 was still better, but we could also, if we wanted to, have run this on the, we could run our 1 versus 1 on the rescaled one as well if we wanted to. All right. Now let's explore. So I mean, we could have. Well, I'm not going to do that, but we could also have done that and see how that worked out. Now let's explore. Let's get into actual error analysis. Let's explore ways we can improve our model, right? I mean, actually, we're not going to actually improve it, but let's look at strategies we can employ to basically find out what's weak in our model and possibly talk about certain solutions there, right? Certain solutions there. Now, let's start off with our confusion matrix, right? Our confusion matrix is going to have what was the true positives and all the false negatives, right? Boom. So I'm going to use my predict MS one. I'll use that one. Perfect. And I already have my confusion matrix. Let me just take this whole thing. It's not bad. All right, all right. I'm using the one that was scaled, by the way. Create a variable CNF. And if you type CNF in here, guys, you'll get your matrix. If I copy this, by the way, right? I mean, you can copy it and put it in there, but right here, you get a nice array. And you should get something like this. I believe I get something like this, very similar, 573, whatever, 455. Okay, something very similar. So you see this, you have this. Excellent. You guys will have something similar to this. Now, from ABI, we talked about this. What was the law we talked about when we're doing analysis like this? Your mind can't process all these numbers, right? You can't process all these numbers. Miller's law, remember that? What's a great way to deal with this? Now we get back to the color maps in Matplotlib, right? I'm going to take CNF and I'm going to graph it with a certain color mapping. In this case, I'll take gray, and I'm going to plot it. And when you plot it, your confusion matrix here, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 going across. Boom. Each number now gets equated with the color. In this case, you know, the larger the number, the whiter the cube. The smaller the number, the blacker the color. All right? Relative to one another. Relative to one another. These numbers are these magnitudes are happening relative to each other. Relative to each other. That's the way it works. Okay? So this is what the color mapping comes in. And again, I could choose a different color mapping if I wanted to. I don't have to choose gray. There's tons of them in pandas, right? So let me go ahead and graph this and let me show you what I'm talking about. So I know some of you guys like to be a little more creative. Use any color mapping you want. So this will give you the gray version. And again, there's another one called Spring. Actually, there's so many of them. If you go online, they show you all the different libraries for color maps. So if I choose Spring, I get a nice color one like this, right? And again, same principle. The yellows are the largest numbers. The more yellow, the larger the number. And the more pink, the smaller the number, right? So, all right, cool, excellent. Now, right now we're looking at counts. That's great, right? And you can see subtle lightness in here. I don't know if you can see it or not, but in your machine, maybe you'll be able to see it. But we want to look at, we don't want to look at actual values. No. We want to look at percentages, right? We want to look at percentages. We want to see how many percent of, because again, look, these are whole numbers, but let's say one class in our training data had a whole bunch of numbers versus another class. Let's say there was a ton, like 10,000 in 0, but the class 9 only had like 100 values. The box, hypothetically, and even let's say it only had 100 values, right? And it had perfect prediction. It had perfect prediction. Meanwhile, 0 had 10,000 values that was trying to predict, and it had 50% prediction. That would still be 5,000 versus 100 or whatever, and this would be like black, and this would be like white, and it would say, oh wow, this was predicted very well. This class versus this class was predicted very well, which is not the case. So we really don't want to deal with whole numbers. We want to deal with percentages, ratios, always, right? Now, so what do we do? So basically, each row, what we want to do is for each class, the actual predictions of each class, we want to convert it into a percentile. We want to convert it into a percentile. So basically, if the first row here is the 0 class, I want the summation of all the actual zeros, right, which is basically going to be the addition of this whole row. And I want to divide each one of these numbers, the 5, 7, 3, 3, the 3, the 18, the 10, by the total number of actual zeros. And then it'll give me a proper percentage, right? How much percentages were actually predicted correctly, how many percent-wise in my zeros were predicted to be 1s, how many of the zeros were predicted to be 2, and so on, so on, so on. And now you can compare these percentages across different classes once we do that, because it doesn't matter that, hey, there was 10,000 zeros in our training data and only 100 9s. Because we converted to percentages, we can now see it apples to apples, all right? So that's the whole logic behind it. So what we want to do is we want to, again, divide each of the rows by the sum of the rows. And there's a cute little trick to do this in Python, right? First things first, we want to create a two-dimensional row sums, right? Two-dimensional row sums that's going to look like this, right? And the reason we want to do this is so the math happens more seamlessly. The math is more consistently. And I'll explain that in a second. First, we want to call the sum function. But now we want to get a little bit fancy. We want to basically say axis equals 1. And that basically it's saying, hey, now do this sum. Let me show you guys here. Now do the sum. If I just do the sum, it's going to add up all the values. And what do you see? 60,000. Why 60,000? I have 60,000 rows of data. All right, cool. But I don't want the summation of all my data. No. I want the data. I want the summation to happen row by row, right? I want row-wise sum. All right, so now the sum, we want to do it by row sums, right? So what am I going to do? I'm going to say axis equals 1. Now what does this do, guys? This basically now, instead of summing up all the values in the confusion matrix, it's summing it row by row by row by row. Sweet. And if you notice, we get a nice little array of values, right? Look at that. Now, we need to add an additional parameter, and that's what I do here. That says keep dims equals true. Keep the dimensions of the original table that you're adding up. Keep the dimensions of the original table. And why do we do this? We do this because we want a 2 by 2. We want our results in a 2 by 2 array. Oh, I think I have to write true. Yeah, you have to do true. There we go. Right, and notice over here now, if you guys can see here, you see, you get a proper two-dimensional array. Granted, in each row, it's just one single value, right? It's the single values from here. the single values from here. But the reason why we preserve the dimensions is because, right, when we're doing vector mathematics in NumPy array, guys, the dimensions matter. So this way, what happens is when I divide in this next line, when I divide all of the matrix by the row sums, right, I go ahead and I put this two-dimensional array into this variable, right? And then what do? I divide the whole confusion matrix by row sums. And now what's going to happen is, because I preserve the original dimensions, the way this gets interpreted is, okay, cool. Right? This table has 10 rows of NumPy arrays. It's a 2x2. It's a 2x2 NumPy array with 10 rows. This is a 2x2 array with NumPy rows. I'm sorry, with 10 rows. When I say this divided by this, what's going to happen? It's going to divide the first row here by the first row here, the second row here by the second row here, the third row here by the third row here, etc., etc., etc. So what ends up happening here is the total for each row gets divided by the values in each one of those, by the respective row, which is exactly what we want to do. That's why we did that little trick, a nifty little trick. All right, and so now I can do this, and I can apply it. All right. Go ahead, create a new confusion matrix that's totally turned into percentages. I run that, and you do CNF&P. It's going to be kind of messy, but you notice it's now not numbers, it's like decimal places. All right, cool, excellent. Now if I graph this, all right, let me go ahead and take this. I'll take the grayscale again. And I graph now CNF_P. Okay, cool. We changed this to percentages, but there's not much difference in the graph, right? In the box, I do see slightly different. Maybe some ranges are a bit lighter, but there's not much difference, right? How do we get this graph to give us more nuanced answers? Remember, the way the color maps work is that it's based on the range of values within the data that you're analyzing. All right. The largest numbers, which is our diagonals, the outliers, they are the correct classifications. But those numbers, those correct classifications, that's fantastic. We want to see that. But because those numbers are so large, they're drowning out any nuance in the other errors. Anything off that diagonal is a mistake. And we can't see where and how the mistakes are because of the fact that the numbers in the diagonal are so much larger. This is why what we want to do is, let's get rid of the right answers. Let's get rid of it. How do we get rid of the right answers? You make that diagonal 0. You make that diagonal 0, it's going to be flat out pitch solid black. But now what we do is when we make that diagonal 0, we got rid of our outliers. And now the color scale is going to readjust based on the existing numbers, which will be slightly more nuanced, and we'll get slightly a better picture of what's going on. All right, here, how do we do it? NumPy, when I talk about making all the diagonal values 0, you can roll your eyes at that, but again, NumPy gives us a function to do it. NumPy has a function called fill_diagonal that literally you could place the square or whatever you got data container in it, and it will literally take that data container and diagonally fill in all the values to be what? 0. In this case, 0, or whatever value you want it to be. In our case, we want it to be 0. Doesn't get any easier here, guys. Doesn't get any easier to do this. All right. I go ahead, I run this function, and now I plot my graph again. And now, as you saw in my slides, oh baby now, right? We get much more nuance going on here, right? Much more nuance going on here. Notice the diagonals now are all pitch black. Why? They're all 0. Because now they're all 0s, the other percentages are now allowed to shine when you're doing color mappings in the scaling. They've now become the new outliers, and now we can see them clearly. Now remember, right? Remember that The whiter the box, the larger the number. Now these are, the wider the box, the larger the number. And the blacker the box, the smaller the number. And remember, anything off that diagonal in a confusion matrix is a mistake. It's something that was predicted incorrectly. All right? Now remember, your rows are your actual values always in your confusion matrix, and your columns are always your predicted columns. All right? Now, from here, if we look at columns 8 and 9, what stands out at us? And again, look at the brilliance of this in terms of analysis. And again, I'm using black and white. By all means, some of you guys, black and white is not your thing. Choose a different color, right? If I go ahead, let me go back here really quick, just for kicks. Just for kicks. Throw a spring back in there. Right, maybe you need a different color scale. Maybe spring and black white aren't doing it for you. Maybe there's another color scale that does it better for you, right? In terms of differentiation. Everybody has their own range of colors that they're better, that's easier for them to see or not. But what I can see in terms of lightness, if we look at the classes in terms of lightness, these columns right here, first of all, these columns right here are light. The predictions of the 8s and the predictions of our 9s are relatively light in these ranges right here and right here. And again, if we look at the actual values too, the actual values seem to be, 8 and 9 seem to be light as well, right? This basically tells us what? There's a lot of errors in terms of the 8 and 9s. Our classifier predicted the 8 and 9s not too well, not too well. The zeros, and for most of the case, 1s tend to have the best classification, and we saw that because they're the darkest rows, and we saw that when we were looking at our precision and the recall, right? Now, what boxes just stand out at you, right? The 3 or 2 brightest boxes in this case are when you are this one, and I would say this one down here. I mean, there's a couple of them that are pretty bright, but those 3 seem to be really white to me. And here what we have basically is we have a situation where the 3s are being predicted. Remember, the rows are actuals. This is 3 right here. This is the real 3s. And right here, for some reason, a lot of the 3s in our classifier are incorrectly being predicted to be what? 0. We have the scale down here, right? So here's the 3. Down my bottom is what? 5. For some reason, the 3s are being predicted as 5, right? The other white box, no surprise, the 5s, right? The actual 5s right here are being predicted to be 3. Right? So there's something going on with the 3s and 5s right here. Right off the bat, we can see this visually. How the heck were you going to notice this in the actual confusion matrix? You weren't, right? This is analysis. This is visual analytics in play, people, right? Again, for my my students, remember, this is a business class, right? You're sitting in front of management. You're working with actual data scientists to to create the proper model to do some sort of project, right? Some analysis. Before you even go to management, you're looking this stuff over. You're looking at the analytics of this stuff over. See how I did that? Business analytics. To say, okay, we need to work. We got some situations here with our classifier. We need to work on this, right? Obviously, starting with the better classifier is the best. Is obvious the first way to go, right? Maybe we already saw that maybe we should be using random forest to do this project. But anyway, just go with it, right? And down here, let's go down here. Let's go to the 9s. So the 9s, for some reason, are being, the actual 9 values, for some reason, are being confused to be 7, right? Which is funky because in my slides, when the first time I ran this analysis, my sum digit was a 9. And my result I kept getting back was 7. I'm getting 4 now in front of you guys, but I kept getting a 7. And actually, if you look at it, the next lightest one here for 9s is what? It's 4. It's 4, right? You can't make this stuff up. It's right there in front of you. All right. Now, in terms of data science, we're not gonna actually execute these solutions, but some possible solutions to the 8-9 shortcoming are what, right? These massive column situations, right? They didn't work as well. It's possibly to the classifier. Remember, we're using off-the-shelf algorithms, but maybe adding to the algorithm another functionality where you're counting the loops that you see within the images. For instance, 8 has 2 loops. 9 has 1, 5 has none. So maybe, because 8 and 9, they do have loops, 2 and 1. Maybe if we start counting up the loops and add that to our algorithm, right, we can start getting a better classifier. Another possible solution for the 5s and 3s could be to this is something called pre-process the images so that they are more centered, right? The reason being because if you look at a 5 and a 3, right, what the hell is the similarity between a 5 and a 3? We can, in the next slide, you guys will see this, right? It's basically the only similarity, if you want to think about it, is maybe the bottom part has the only thing that's similar. It's the top part is different. The top part is different. The 3 curves like this, the 5 goes straight up and to the right. That's if there's a confusion, right? It is for somehow it's not making the differentiation on the top part. The bottom part is the same, but the top part for some reason it's not making that differentiation. Maybe if we centered the numbers and shifted them all the way to be vertical, the classifier can clearly see that, oh, this image top line is going to the right. This for the 3, the top line is going to the left, right? For some reason it's messing that up. So maybe there we would actually have to go through our images and reshift them and mess around with that. All right. Now let's actually check out some of these images. Let's check it out. How do we check out some? Let's check out the first misclassified 3 and the first misclassified 5. So I'm going to do the 3 one first. How do I do that? This is the third time I'm showing you guys this trick. The third time I'm showing you guys this trick in so data train obviously has our actual images, right? How do I get all the ones that are actually 3 but were predicted to be 5s? This is the third time I'm showing you this trick. We are going to use the Boolean logics from other data containers within the data train slicing. So here, first things first, notice that I have 2 conditions, so I have to use parentheses, right? That's a refresher. Target train, data train, and predict underscore ms. They're all the same. They have the same amount of rows. Their columns are different. Yes, you're right. The column amounts are different, but their row numbers are the same. But in data train here, I'm not specifying any column. No, you don't see any comma there. I'm simply selecting rows. So this will work. So this is saying wherever in data train the row is true and the row is true, give me that data train. That's basically the way it works. It works literally. The first row in target train is looking at the first row of data train. The first row in predict underscore ms is looking at the first row of data train. So what this is saying is, hey, if the first row of data train is actually a 3 value, and the first row of predict underscore ms is a 5, the value was actually a 3, but it's predicted to be a 5, then give me the first row of data train. That's how it works. That's how it works, right? If any one of these conditions right here are wrong, it's not going to give you that row of data train. And so A3 underscore, again, A stands for actual, P stands for predicted. Actual 3 predicted underscore predicted 5 is going to give you all the images that were actually 3, but were predicted to be 5. Okay? From here, I create another variable, and I simply take out of that set just the first array, the first image in that set. Now here we're doing just like we did before with our sum digit. I take that first image, I reshape it into a 28 by 28 NumPy array, so I can call my image object and convert it into an image I1, and then I graph it. I'm show I1 plot, boom, and I get this 3. All right, and I get this 3. This is a 3 that's actually a 3 that was predicted to be 5. And we can see possibly why it made the confusion, but there's a clear bar up here. There's a clear bar up here. Right? Now let's do flip. Let's flip the side. Let's flip it. Let's grab a 5 image that was misclassified as 3. And again, I'm going to do the same analysis. I'm going to say, okay, where was my target train equals 5? And where's the corresponding prediction equal 3? Give me all those images. I put in A5 underscore P3. I'm going to take the first image out of there, put in this variable. I'm going to reshape that image into a 28 by 28 NumPy array, and I'm going to make that NumPy array into an image, I2, and I'm going to plot that, and that plot's right here. Okay, now look at this, guys. Wow. This part right here and this part right here are scarily similar. All right, so I can see where the classifier messed up. But there's a bar up here. Right? There's a bar up here. How did it mess that up? Now, in terms of going back to what we were talking about before, dealing with the 5s and 3s, maybe if we center them and reshift them. So maybe if we said, okay, I mean, these guys look pretty much centered in the image. Maybe we can rotate it a little bit so that, so this one doesn't seem like, this seems like it's vertical, but here the 5 seem like it's slightly on an angle. So maybe we could rotate these images. Again, this is part of data wrangling. We would go back and add to our data wrangling process of shifting, finding images that are like diagonal like this. And how would you do this, guys? Theoretically, how would you do this? Maybe I should make you do a project on this. Is that you see this space will have all zeros. This space will have all zeros. We want the zeros to be more like this. We want equal padding zeros on both sides. So we would apply some sort of funky little algorithm to shift it so that the image shifts, all right? So it's more vertical, all right? But then again, still, guys, how did the SGD classifier mess? There's still the clear line over here. How did it mess it up, right? What's happening there? This is where you have to understand your classifiers, right? The SGD classifier, right? So, and this is the conclusion now of the lab at this point. We, finally, so the conclusion here basically is that, look, we use SGD classifier, but we solve for random forest classifier works better, right? The classifiers that are chosen in machine learning, they matter. And the way they work matter. In SGD classifier's case, it's a linear model. It's a linear model. It's a linear classifier model. All it does is assigns a weight to each feature, each pixel, column of pixels, right? And when it classifies a new image, all it does is it takes those scores, those weights of those numbers. It takes the weights and the actual pixel value in those columns. It adds it up and it gives a score. Since 3 and 5 are so similar over here, right? All these pixels are getting scores. All these pixels are getting scored and adding up. The only scores between 3 and 5 are this one. So 3 has these additional scores right here, whereas 5 doesn't have them, right? But it's only but because it's only a few pixels off between that line on top and for 3 and not for 5, the classifier produced similar scores for both of them, right? Because it's only off by this much amount. And because the scores are similar, from there, you're getting those results, right? You're getting those results. Now look, if we did we use the rescale data, but we're still using the SGD classifier that's defaults to 1 versus all. We didn't do this for the SGD classifier 1 versus 1 with the rescaled image. So maybe that might be better. I'll leave that to you guys to check that out, right? But nevertheless, that's the way SGD classifier works, and that's why it makes total sense why in this scenario 3 and 5s are being mistaken with one another. Okay? So at this point, we're done with our finally lab 5. And the next step is we're finally ready for a practice set. And after that practice set, then we can start talking about our midterm. All right, guys? All right. Have a good day. Hope you enjoyed the video.